Back on day 10, we successfully broke our massive application down into 100 independent microservices. The backend engineering team cheered. But today, the mobile developers are panicking. Their front-end applications are completely freezing up. Let's look at the hidden background process of what actually happens when a user taps to open a standard e-commerce product page on their phone. Because our backend is chopped into so many distinct pieces, that single mobile app has to independently reach out, ask the pricing service for cost, the review service for ratings, the inventory service for stock, and on and on. We call this the Chatty client problem. Forcing a mobile processor to make 50 separate round-trip network requests over a spotty 4G cell connection takes a massive toll. Every single one of those requests adds noticeable latency, and running the radio antenna constantly drains the device's battery. It is time for a reality check. When client devices talk directly to microservices, your system architecture stops looking like a clean blueprint and starts looking like this. By optimizing our backend for engineering flexibility, we accidentally passed the complexity costs directly onto the user's device. We traded a backend monolith for a fragile, highly coupled mobile nightmare. We fixed this with a new layer, the API gateway. Instead of 50 separate connections, the mobile app makes one unified call. The gateway then takes over, rapidly querying the internal microservices, gathering the dispersed data, and packaging it into one neat response. The API gateway acts as a high-speed network aggregator. We take the heavy lifting off the user's weak cell connection and shift it entirely to our ultra-fast internal backend network. But aggregating data is only half the job. Every large system has cross-cutting concerns. These are system-wide rules, like security and user authentication, that every single service requires, but absolutely shouldn't have to build for themselves. Here is the kicker. Remember back on day 17 when we built a rate limiter to prevent massive traffic spikes? The gateway is the perfect place to deploy it. It serves as the ultimate bouncer for your network. This diagram illustrates the defense mechanism. Look at the rate limiter middleware acting as a barrier. When malicious traffic floods in, the gateway intercepts it, returning a red HTTP 429 error. This rejects the requests before they ever reach your fragile internal microservices. Because the gateway handles that incoming traffic and also takes care of verifying passwords and terminating secure SSL connections, we get to strip all that repetitive code out of the backend. The gateway pulls double duty as a traffic router and a centralized firewall. This allows your 100 internal microservices to focus purely on executing their core business logic. However, deploying a single massive API gateway introduces a new bottleneck when you have drastically different client devices. A 65-inch smart TV and an iPhone require completely different types of data. Treating them exactly the same leads to an issue called stamp coupling. This is the huge waste of bandwidth that occurs when a generic gateway forces a heavy, desktop-sized data payload onto a mobile device that only needs to render a few lines of text. To eliminate that waste, we refactor the architecture using the Backend for Frontend, or BFF, pattern. Instead of forcing everyone through one monolithic gateway, the BFF pattern splits the routing by building specialized gateways tailored to specific client types. Now, a sleek, narrow pipeline routes a tiny, optimized data payload straight to the mobile app, while a heavy-duty pipeline serves the massive data streams required by a desktop application. By utilizing the BFF pattern, every device gets exactly the data it needs to render its screen, no more, no less. We achieve a clean separation between the endless variety of front-end devices and the complexity of the back-end code. Now our front-end is fast and clean. But if we have 100 microservices talking to each other, how do we find a bug when one of them silently fails? Tomorrow, day 31, we dive into distributed tracing and logging. Hit subscribe.